people were asking where can we get the slides. I put them on my personal wiki.hsr.ch, and then my name. That should be sufficient, Peter Sommerlad. You might also Google my name, and this should show up. And there's a page with the slides that I might show. I will not be able to show everything, but that's a collection I prepared for this session. And just to give you a very important page once we're in the browser, cppreference.com. That's, I would say, currently the most current and not too badly explained collection of the standard library features. And you should take, and especially it marks also the code with from which version on it is available. That's like, say, unordered map that we have seen is only available since C++11. And I like you to take a look at the algorithms library. And you see these are a whole bunch of algorithms, several pages full of algorithms. And that's only part of it, because there are more. If you go to the numerics library, where there are more algorithms, and only these few, but especially accumulate and things like adjacent difference might have use beyond just numerical computations. Oops, that was one too far. Here we go, CPP. So cppreference.com. Now, let's get back to my slides. And I figured out with Mauro I should continue first with this talk before we switch over to more details on how to define your own template classes. Okay, what have we seen? We can actually parameterize algorithms with function objects or lambdas. And if we want to store these things or do something more with them, there's a whole bunch of infrastructure in the library where we can actually store function objects or define our own function objects on the fly. And just as a little background, in C++ you can overload operators, and you can also overload the function call operators. And the class that overloads the function call operator is called a functor. The lambdas that we have seen will all be internally transformed into such a class where the call operator, the function call operator, is overloaded. And we have regular functions that you can pass as an argument to an algorithm, lambdas, or your own function objects, or you can keep those things around. And there's a thing called function, std function, that you can use to store either of these things that can represent a function in a variable. For example, to pass it on later to an algorithm, or to call it for your data. So standard function actually is a template class, and it takes the call signature, how you want to call that function, as its template argument. So it's not only giving a type, it's giving a function type. So with a return type and parentheses that list the parameter types. And since it can be used as a variable, it can be default constructed, and a default constructed function object of std function type will be empty. That means you cannot call it. If you used to program in C, you might have used function pointers, and if a function pointer would be a null pointer, you cannot call a function through the null pointer. That would be undefined behavior. And again, with the function object, it could be empty, and you cannot call an empty function object. Again, that would be undefined behavior, but you can check for that emptiness by comparing it or by checking it against the null pointer or using it as a truth value in a conditional expression. So what what can you use it for? For example, if you do reactive programming, you can use set function to store callbacks that you later call whenever an event gets triggered. And you can also exchange the callbacks because you can exchange the function objects. Another thing that function is actually doing, you can keep the results of so-called bind expressions, and we come to that in a minute, or you can keep lambdas there. For example, if you define a variable, initialize it with a lambda, you have to use auto as a type specification. The problem is you cannot reassign another lambda expression to this variable because its type is distinct from the original lambda, even if it has the same signature. If you want to keep a lambda in a variable that you can exchange later on, you would use std function for the variable type. Now, example code, that's what I was waiting for. Let's use that one. You see here, you say this function object holds a function that returns a bool and takes an int as a parameter type. So an int argument returning a bool, and we name it odd. And to check if it's valid, we can use it in a Boolean context. And if it's false, so if not odd, we say it's empty. And since it initially default constructed, it's empty. So this will actually output odd as empty. Now we can assign it a lambda that actually takes an int and returns a bool. And then we will see that odd is actually defined. And now we can call it, because it has an overloaded call operator, and pass in ints and see what the result is as a bool. And the output would be 3 is odd because 2 is even, as we see. Anybody use that? Microphone?
I have not understood the motivation for checking if the function is valid.
What is the motivation for checking if the function is valid? Well, it might be uninitialized, so it's default initialized and it's empty, and it's no longer valid. Or it's you might actually reset it to this uninitialized state by assigning a null pointer to it, which would be equivalent to the function pointer that is null, and then it's invalid to call it because it's empty. There's nothing to call out for, and that means it's empty and you cannot call it. That's why you have to check it. For example, if you use std function as a member variable in some kind of infrastructure where you want to store a callback function, then a user might not have provided a callback yet, so it's empty. So before you call it, you have to check if it's empty. In most cases, you would use it in a way where it's always initialized, and then you don't have to check it before you call it. But if you can reset it, then you better check before you call. Not is an alias for the exclamation point. That's deliberately on this slide to trigger a question like that. Exclamation mark is the syntactical syntax for logical not, and you can spell out the logical operators as text. That's standardized, but nobody uses it. But it's possible, and I just put it here to trigger that question. So you would usually use if exclamation mark whatever to check if it's false. And you see here I used it without the negation, and it's again valid in the Boolean context to have it use it like that. So we also have and or as syntactical alternatives for double ampersand and double vertical bar, which might in some cases make code a little bit less error prone, because at least they won't you won't mistype them just a single ampersand, meaning bitwise and, which is still most often syntactically correct, but might not be semantically what you want to get. Now, function binders. In C++03, there were a very crude version of function binders. And in C++14 with variadic lambdas, you almost no longer need them. But nevertheless, I explained them. What are function binders? Function binders take a function or a function object or a lambda or whatever and define or change their arity. So they might fix a specific argument and keep another argument open. They can also be used to combine function objects. So call one, like create a new function object where calling one gets the argument of calling another one, and then make that a combined function object. I use them most often with standard function object classes. The standard provides function objects for all kind of unary and binary operators. So for every operator that you find in the language, almost every operator that you find in the language, you get a corresponding class in the standard library, in the header functional, that implements this operator as a function, as a functor, so it implements the call operator, calling out the underlying operator. Like multiplies takes the binary multiplication operator to its 2 parameters and returns the result of multiplication. And it does that in a generic way, so you can pass any type where the multiplication operator is defined to that function object. And you can use that function object as an argument to the algorithms that we used. There are also function objects for all kind of relational operators, like std_less would compare two values with a less than operator and return the result of the comparison. And std_less is used, for example, for set and map as the comparison of the elements or the keys in the data structure to sort them correctly. Now, function binders. You can change the arity, you can combine functions, and if you have a function that requires a reference, like a stream object, for example, that you only can pass by reference, there are additional wrappers called ref and cref to actually construct a copyable type that is actually underneath has the reference of the underlying variable. Bind. If I change the arity, I mean you can have a binary function, two parameters, and change that to a unary function by fixing one of the arguments. And to refer to the remaining free parameter that still has to be provided, you use so-called placeholders, and they have specific names, _1 and _2 and up to _9. I believe that's at least not very useful if you write a function with 9 parameters. That's a not very nice API. If anybody had the bad luck of you to use the Windows APIs in C or C++, they suffer from that many parameters, and they are horrible to use. And that was since the beginning. When I've seen Windows 1.0 in about 80, when was it? 30 years ago, about roughly. 85, around 85, I was, I told to myself, I will never be able to use that API. It's just too complicated to use. And it's still the same. At least people tell me. So But here we have _1 and _2 are useful. So if I have a binary binary function, and the result should be unary function, I would only use _1. If I have, let's say, a ternary function and would want a binary function, by fixing one of the arguments, I use _1 and _2. And with C++ 14, the use of bind is quite less important than in C++ 11, because I don't have to specify the type of the remaining parameters that where I have the placeholder types _1, _2. And with generic lambdas in C++ 14, I get the same capabilities that I get with bind in C++ 11 with respect to creating on-the-fly function objects. Example code. I need the header functional, and to make syntactical good use of the placeholders, I use using declaration. I could either use using namespace placeholders or using namespace std placeholders, or I could refer to a specific one like using placeholders _1. And here the using namespace std is, let's say, excusable because it's in a local scope, it's not in a global scope. And again, that's bad code because the main function uses a lot of code that's untestable. So hit me. I create a vectors with place for 10 numbers. I initialize that vectors with the numbers 1 to 10 with iota. Anybody of you knows how to program an APL? Programming? Then you know where iota comes from. That's the iota Greek character is a symbol for getting some kind of. Huh? That's more than 30 years ago. I don't know how to program an APL. I only know that it exists. But iota is that's where the name of that function came from. It just initializes a range with succeeding or the ongoing values always incrementing by 1. And if we output this list of numbers using a copy algorithms, so we take the vectors begin and the vectors end, and using an O-string iterator to output it, and blame me, I use endl, old code, old slide. We see we get the numbers 1 to 10. Now we use the transform algorithm, which also is a copy with on the fly applying a function to the range that is the input range. So we have the transform, again the vector begin and end as the input range, the output iterator as the output range, like we would use with copy. And now we create a function object on the fly using bind and pass this function object to the transform algorithm. Because this version of transform with a single input range uses a unary function to apply to each element of that input range. And we construct that by using the plus function object, which is actually adding two numbers or adding two things. Anything that has a plus operator, binary plus operator, can be used as the type, the template argument of the plus here. And we say, okay, the first thing that goes into that plus call is actually still a parameter. That's a placeholder _1, a unary function, so _1 has to be present here. And the second thing is we fix with the value 10. So this bind call creates a new function object that in its body calls plus, and it passes a single argument that gets passed into the created function object, and as a second argument to the plus call, it fixes the 10. And as the output for each element in the vector, we get the element added to the element. We don't change the vector, we just apply that function while copying the elements of the vector to the output stream or somewhere else. The second version of the transform, the second call of the transform does something else. It again changes the arity of the multiplication functor, multiplies. And it repeats the placeholder. So the single argument that is passed to the resulting function gets used twice as an argument to the multiplies functor, and that will actually produce squares. And because it's in the transform call, it will be not change the vector, but actually while copying the elements from the vector to the output stream, it will apply the squaring here to the elements. Mauro.
So I guess many of the people here are HPC people, so they might be wondering if there is any performance penalty in doing this.
Not that I know of, because everything gets inlined in the way. And if you use the lambda, it will be inlined anyway.
Yeah, this is also my experience. I run specific benchmarks to try to see if this is happening. And this is, if you think how bind could be implemented, it becomes quite obvious that the compiler can inline everything, and it will be efficient as just doing the plus and multiplication in a loop.
There's no penalty to pay because everything is inlined. And the compiler can optimize any superfluous thing. And if the target wouldn't be a stream iterator, it might even vectorize it. Let's get back to our multiplication table. Again, our multiplication table that we've seen with the lambda could also be implemented with the bind, and that's just for showing off. It's possible to use bind here as well. And this is the case where we actually use a lambda and a transform. And that's, let me check where the lambda ends here. So that should be C++14 code, because it has multiple statements within the lambda. Does it have? Yes, yes. Yeah, don't want to say anything more. Maybe one thing you might ask, okay, here I'm returning a vector by value. Is that a problem? Is that a performance penalty I have to pay? Usually, the compiler will optimize, it's so-called return value optimization. So returning a local variable by value tends to be very efficient. Even before C++11, but with C++11, if that type provides a move constructor, it will use the move constructor anyway, and it will be, even if it cannot do the return value optimization, it will be return with a move, and that will again be efficient. You might correct me if I'm telling bullshit, but it will not. You will not have to pay a penalty on that.
There is one thing is called a copy elision,
Yeah.
which happens, and it might require your class to define the a move constructor, but it might not call it, which means that you should never have move constructors with side effects, because they might not be called, even though they are required to be in place.
Actually, this is called in a context where a temporary is passed to the function print times, and the compiler will generate a code that will create the return, the value passed to the function exactly in the position or in the register where it's passed to the function, and only once no copying done by the code, but actually required. Copy or move is required to be available. Otherwise, you cannot call it. So you might get a syntax error if you don't provide it. If you provide a copy constructor or a move constructor, it will never be called, but still you have to provide it. Okay, we've seen a lot of things. And one last thing I've already referred for, you can use initializer lists. This has to be homogeneous values as the right-hand side of a range for. So if you have a few values you just want to do something with, you can write a range for with just writing down these few values. And the trick is that the range for is specified by calling begin and end with the element on the right-hand side of the colon. And begin and end have standard overloads for all standard containers. They call out to the member functions if they are available. But there are also overloads in the standard namespace that work for arrays. So a plain array you can use there, even though I recommend that you stop using plain arrays and use std array instead. Memory. Who has used new in C++? Who is using delete? Who has never made a memory leak? Or never referred an invalid pointer? You might recognize if you do double deletes because that usually leads to a crash. The good thing is with C++ 11 and especially C++ 14 on, you no longer need to call new or delete yourself. There are a lot of classes around that actually will do all the memory management on your behalf. String is one of them, and vector is the second most important one of them. Anything else, if you want or need heap allocation and don't have a standard library class, a container doing that for you, you use either unique or shared pointers to do so. And you have factory functions, make shared and make unique, that will do the allocation in the most efficient way and will automatically clean up everything after you so you won't produce memory leaks. And that's why I recommend to everybody no longer write new and delete in their own code. There's no reason to do so, in my opinion, unless you're an implementer of a standard library or a very sophisticated library where you might use placement new, for example, to do something interesting. But if you have never heard of placement new, good. You will never use new again anymore from today on. There's also something else. In C++ 11, there's a value called nullputter, N-U-L-L-P-T-R. And it's a replacement for all kinds of use of the macro null or any zero as a pointer value, meaning the pointer that points nowhere. There's no longer the need for using null or zero as a non or nil pointer, null pointer. Use nullputter as a name. It's a constant in the language with its own distinct type. So there are even specific overloads based on that type if the nullputter is used, and that's specific.
Yeah, how is the null pointer implemented? Is it just kind of a special, is it actually zero in that case, or?
It will compare equal to 0, because that's for legacy compatibility. But from the compiler perspective, it's a distinct value and a distinct type. And you just don't need to know that it's 0. And it has the advantage if you just write 0, that's from the type is actually an int. So there's a kind of a tricky implicit conversion from an int to a pointer with a 0, which is kind of a rough edge in the language. And with the null pointer, it's defined a valid assignment to a pointer. If you use null pointer, assign it, it's empty, it's founded. The default value of a pointer is also null pointer, but it's not 0 because 0 could be an int, and if you add something to an int, you might get a 1, which is not really a very good, well-defined pointer. And you should also initialize all pointers with null pointer to denote, if you cannot initialize them to some specific address, because then you know it's not pointing anywhere. If you have just an uninitialized pointer that might point everywhere, it might be a valid address or not. You're lucky if it's an invalid address, then your operating system might just terminate your program with a signal. But if it happens to be a valid address in your address space of your current process, just by chance, that's hard to track errors. There are two kind of smart pointers in the standard library. One is shared pointer. Shared pointer has its use in code that is, let's say, using OO semantics with polymorphic types, and where you actually have multiple references to a single object on the heap. It implements reference counting. The reference counting itself works across multiple threads. So if you share a shared pointer value across threads by copying, then the reference counter will work. There's no guarantee that the pointer to object is actually protected. If you access that from multiple threads in a mutating way, you get undefined behavior unless you protect that with a mutex. And there's another version that is more efficient. It's called unique pointer, and that is actually if you don't need to share the objects, or don't need to, at least you have a single place where you keep the ownership. It's where you keep the unique pointer, and once you release a unique pointer or forget it, the underlying objects that are on the heap get destroyed. There's also an omission in C++ 11. We forgot to standardize make unique. I'm not sure it was deliberate. I think it was just forgotten. In C++ 14, we have make unique, so you no longer that will do the allocation and the initialization of an object. For make shared and make unique, you can pass any constructor arguments that you would be able to pass to the underlying type T that you create. And typically the return type you store in a variable that you define with auto, so you don't have to think about the details of how to spell it. So you have to spell the type T only once as a template argument to make unique or make shared. When I made this slide originally, I hoped that std optional would make it into C++ 14, which it didn't. It's available in the experimental namespace in some compilers, but the Boost libraries have an optional. And why did I put optional here? A lot of code uses pointers to denote, or especially pointer return types, to denote that something succeeded, then the pointer points to that something, that the result, or that the computation failed, and then the function returns a null pointer. Anybody use such an API? If you anybody define such an API? Lucky guys or not? Don't do that anymore. Use optional to return by value, and optional has an indication if the optional is empty. No longer use pointers for that. Because when you have a pointer API, where a null pointer means, oh, it failed, and a valid pointer means, okay, here is the value, you always have to question, the user has always the question, what do I have to do with the pointer, the memory the pointer points to? Do I have to free it? Do I have to delete it? Do I have to just do nothing with it? And it will be cleared up? what happens in case of an exception if I forget to delete it or don't delete it. So APIs returning pointers to values to mark it might succeed or not should no longer use pointers for that. They should use optional. Boost optional today and standard optional in 2017 for that case. And return by value, because then there's no memory to be managed. Everything is passed in as a value, so nothing bad can happen. If you have never had to use an API using pointer returns to denote a potentially failing case, you're lucky. Okay, null pointer, I explained everything about that. A typical resource management, that's a contrived example, so not very useful. You might have a factory for A objects. This is a very simple class A, taking a constructor with 3 arguments. Just to show you, if you call make shared A, you have to provide the constructor arguments that you use for an A. And we can return that shared pointer by value. And we can even copy shared pointers, which will increase the reference count underneath. We can copy the underlying object, which would happen here. We can create another shared pointer by copying the copy. And when we get to the curly brace here, all shared pointer variables are forgotten. So they decrease the reference count when they're destroyed. And once the reference count gets down to 0, the heap memory gets deleted automatically. No more new, no more delete. Memory management by magic. So whenever someone asks you, does C++ have garbage collection? The thing you have to write down is, oh, it has a single character garbage collector. And there are even t-shirts saying that, but the spelling on the t-shirt is wrong. It says a single line garbage collector, but the single character garbage collector in C++ is that. Cool, huh? And that's really a benefit of the deterministic lifetime of things in C++, because you know when things go away. If you have class hierarchies with shared pointers, question?
Can you go back to the previous slide? And
the very contrived example.
yeah, so the main you have the first assignment from A factory and then the second assignment. So what happens to the reference counting, especially in the first assignment?
So in the first assignment, I think I need to map a piece. Let's map a piece of memory. Let's say this is our heap, a nice heap. And first assignment, we have a shared pointer variable NA. We call the factory function that actually allocates space for an A here, plus a little bit extra space for the reference counter, 1. We return from the factory, and NA actually refers to this piece of memory, including the reference counter. It stays at 1 because we return a temporary, and that gets assigned to NA, and it sticks at 1. Now we get another shared pointer, B, that we make equal NA. So B also refers to that A, and the reference count goes to 2, because we now have 2 shared pointers referring the same object on the heap. Now on the stack we create a C object that is a copy of what B is referring to. So C is actually its own copy of an A. Nothing to do with the shared pointers. It's a new object on the stack. And in the fourth statement, we create another A object by taking the value of that C and calling the copy constructor and putting the space here, and that has also a reference counter with the value of 1. Now comes the garbage collection. The local variables, and we have another referring to that. Now the local variables get destroyed in the reverse order they were constructed. So when another gets destroyed, that reference counter drops to 0. This space gets deleted automatically. When C gets destroyed, it's a local variable on the stack, so it's A gets destructed. When B gets destroyed, it refers to this shared object with a pointer of 2. It decrements the pointer to 1. This object still is around. And now an A gets destroyed. It refers to this object on the heap. This one gets down to 0. And now this gets destroyed when this got destroyed. That's the magic. Now, if you stick to, let's say, local variables, shared or unique pointers, everything works charmingly. You don't have to think about all these things. It just works. Questions?
Could you give an example of make unique also, or you have it maybe later in a slide? Because I used to use
if I would
share,
replace shared pointer with unique pointer and make shared with make unique, the only thing that wouldn't work is actually that thing where you have here with a unique pointer you cannot get a copy of the unique pointer. That would not compile. Otherwise, just replace shared with unique and it would work the same.
So if I wanted to use the same example, I would and replace it with make unique, I would have to create B with its own call to make unique.
Either with its own make unique, which would give you a new object, but you cannot actually copy a unique pointer.
I
What
see.
you could
So it will
do-
be a separate object and not a reference to an A.
Yeah. What you could do is actually steal the unique pointer from A by using std move. That would make an A unique pointer empty, would reset it to the null pointer, and B would now be the single unique pointer to that A object.
I see. Thank you.
Now, using shared pointers for class hierarchies, because I didn't want to invent a class hierarchy my own, I used the O-stream class hierarchy, where I have the O-string stream and the O-file stream, OF stream. And this is again a bad example because I use an API technique that I would no longer recommend to anybody. Boolean flags to switch between different behaviors of functions are very bad APIs. Why? When you call it, you never will know what true or false means. So just consider that this bool is not a bool, but something else. But depending on whatever we pass in, we get either a string stream on the heap or a file stream on the heap. Because I have this polymorphic factory, I need to use something where I need to return a pointer thing, and I opted here to make a shared pointer. And the shared pointer will automatically delete the right subclass regardless of how it was constructed. So, but that would even also work for unique pointers. But then actually the base class has to have a virtual destructor like with regular pointers that you used to. A usage, as you see, only because I named something out and file, you might consider that file is actually referring to a file. And if you look at the code, it is so. But you see that true and false make a very bad API because they do not say what they mean. Now you might ask, how should I do that? Well, one thing is if you have some kind of where you pass a conditional thing in, use an enumeration where you have, let's say, provide file, provide string stream, or some other name that you can refer to instead of true or false. That on the call side, you actually have, you say what you want to get. Like an enum with file and string and pass in that enum to that function would actually make the call side much more readable than it is with true and false. And again, here everything works fine. Shared pointers go out of scope. The string stream is thrown away, and also the file gets automatically closed and the file stream object thrown away. And this is actually a situation where you cannot easily return by value because you cannot return a stream by value. It's not copyable. And because it's polymorphic, you cannot, let's say, return just a reference because a reference to a local variable that you might create there would not work either because that would be a dangling reference, which is the second worst thing since a null pointer dereference. A dangling reference is even worse because it cannot be null, so you might not even be able to detect anything like that. What we need here is, because we return to different types, because the shared pointer of a string stream and the shared pointer of a file stream are distinct types, we have to provide a return value. If we would, may I finish my sentence first? If we would use auto here, even in C++ forwarding code where I could use auto here, it's a compile error because the return statements don't agree on the type that they return. Therefore, we need to specify the base class shared pointer as a return type here. And now your question.
Would it also make sense to use a unique pointer here? Because we sort of only want one owner of this object and then pass the ownership to the next one.
It would work with unique pointer here in that case, but that requires two things. First thing is that the class hierarchy at its root does have a virtual destructor, which is not actually necessary with shared pointer because the make shared will actually remember the original type, so it will know how to delete the underlying object even if the class hierarchy doesn't have virtual destructors. And for a unique pointer, and the second reason is when I made that slide, it was for C++ 11, which didn't have make unique. That's why it's not using unique pointers here. Otherwise, for this example, unique pointer would be just fine. So you can have these hierarchical class hierarchy factories with the unique pointer as well. And if you don't intend to share that, which might not be a bad idea with the stream objects, it's a good. You can use unique pointer perfectly here. And that's a simple example with unique pointer and a factory, and it's safe to return unique pointers by values. It's a temporary constructed at the return statement, and there's always only a single one available. You might take something out of a unique pointer. That's the example I told before with the move. You cannot copy it, but you can steal from this one and pass it over to that variable. So afterwards, pi is actually empty, the null pointer, and pj took over the memory pi was referring to. And the bool alpha will actually guarantee, if I put out the bool, it will print out true or false. And I think that might be worth. Let's see if I have code for that, or do I have the output here? No. To show you the running code of that one. I just switched over my come on. I have so many examples that I that's a different kind of, yeah. Don't be confused by the many things going on here. Okay, here we got our factory. With pi, move, pj, and if I compile and run that, I get the output pi. It's actually 42, which I would expect if I pass in 42 to the constructor of the unique pointer, or to make unique. It's valid. If I move, after I moved that to pj, pj keeps the value 42, and pi is no longer valid. It evaluates to false, so it is actually equal to null pointer. So that's how this stealing from a non-copyable thing works with using std move. And unique pointers semantic actually guarantees that nothing, there's not a second copy. There used to be in the language a thing called autoputter. Anybody used that? Only very few. Unique pointer is what autoputter wanted to be but never got to it, to being that. And we needed to change the language to get that semantic that autoputter pretended to have correct. Unique pointer, you can also use it to manage memory returned by a C function. There are some APIs that return a pointer that was allocated with the C allocation function that you have to pass to the free function to free the memory. And this is an example from my unit testing frameworks. There's a compiler intrinsic called cxademangle that takes a name that is a so-called mangled name and will produce a nicely printable version of that name, how a compiler would actually use it. It's used for function and type names. And this function cxademangle allocates memory using malloc. And this has to be freed afterwards. And to make sure that this happens, I use a wrapper. I use a unique pointer that actually takes two template arguments. The first one is the type the pointer points to. And the second one is the function that is the type of the function that is called when the unique pointer goes out of scope and is destroyed. And I have to, when I construct such a unique pointer, I have to pass in whatever pointer I want the value be, plus the address of the function to be called when the unique pointer goes out of scope. The default behavior would be to call delete on the pointer given in the unique pointer, but this wouldn't work in that case. So we pass in the address of the free function, which is the opposite of malloc or calloc, and we pass in the result of that cxa demangle function in the to be freed unique pointer. And returning such a unique pointer with such a specific behavior would require us to use that long, elaborate type actually as a return value, and that's not very convenient. What we want to get from that function is actually the name of that thing. So we return the name as a string. So we take the pointer out of the unique pointer, which is a character pointer, pass it to the string constructor, which actually copy the characters into a string object, return that string object, and once we're done with the function, our unique pointer, to be freed, goes out of scope, and the free function gets called. And the memory that cxa demangle created for me is automatically freed, so I don't get a memory leak here. And I even don't get a memory leak in case there is an exception. And that's the big advantage of using unique pointer for this. Let's say for some strange reason, the string constructor throws an exception. Maybe because we ran out of memory, or whatever happened, or I do more in that function that might throw an exception. The unique pointer object to be freed gets regularly destroyed even if the exception was thrown, and there's a thing called stack unwinding, so all local variables actually get destroyed, and the unique pointer guarantees that the memory that it's holding on gets freed. And the underlying principle is what is called RAII. Resource acquisition is initialization. So we acquire the resource from cxa demangle and initialize the variable to be freed. And the destruction of that variable actually releases the acquired resource, the memory pointed to by that pointed cxa demangle calls. And that's the principle. Whenever you have some resources that need to be cleaned up, using something like unique pointer or RAII is actually the key to safe programming and keep your memory around. That's why I also tell you never use new and delete, because if you do it manually, you might forget to call delete, or even if you don't forget it, you might get an exception where delete might not be called if you have it in the regular control flow, which will not happen with these smart pointers here, because whenever you pass this closing brace, either through an exception or by returning or by leaving a scope, everything will be cleaned up, no leaks. Take that home. No, just, I think Mauro will be happy if you do that from now on. Okay, there's a third thing that I'm running out of time, I think, for today to explain that. If you use shared pointer in your own classes, for example, as members, to build up circular structures, so where things might refer backwards and forwards, then you end up in a situation where you no longer get to the reference count of 0 when you hit the curly brace or forgot all the shared pointers that you keep on to yourself. In order to break these circular structures, you have to provide at least one link to be a so-called weak pointer. A weak pointer knows its shared pointer object, but it will also recognize when that shared pointer object goes out of scope. So the weak pointer wouldn't increase the reference count, but it will be notified if the reference count dropped to 0 and it's no longer valid where it points to. And using weak pointers, I have some code examples. If time allows, we can show that, but I don't want to go there now. You can actually keep circular dependencies and still get the cleanup automatically. You just have to check if the weak pointer is still valid when you access it. So my rule for resource management: don't use raw pointers or self-allocated buffers on the heap. Use unique pointer, shared pointer, and for data, use vector and string for plain data. And no heap allocated arrays. No raw pointers. Especially no character pointers for string handling. That's, I would say, how do you say it in English? It's a sin you must not commit in C++. Now, remaining traffic signs. Who knows what these things are? Let's start in the upper left corner. What's that for a class X? The copy constructor. Who has written a copy constructor in his or her life? From now on, you no longer write copy constructors, because they are most of the time wrong anyway. So what's on the right-hand side? Upper right-hand side. The destructor. Who has written a destructor in his life? You no longer write destructors. You let the compiler do that for you. And what is this one here? A copy assignment operator. Who has written a copy assignment operator? Should be the same ones who implemented the copy constructor. That's even worse, because it's even more often wrong than the copy constructor. And you also don't want to write those. And now there are two new ones. The middle one, that's the move constructor. It actually takes an object, steals the guts from it, and creates a new one from that. And the copy assignment, the move assignment operator actually takes an object, steals the guts from it, and assigns it to the new one, which it has to release first, if it's not empty. So there are some people who say, okay, whenever you need to implement one of these 5, you have to implement all of these 5. In C++ 03, when we didn't have the move parts, it was the same. Whenever you implement either copy constructor, copy assignment, or a destructor in your class, you have to implement all 3. Or at least declare all 3, even if they might not be callable. I say today, you don't implement any of these, you let the compiler create the right code for you. Because it will create for you a copy and a move constructor, a copy and move assignment operator. Oh, it will not, depending on what your member variables and base classes are doing. And it will always create a destructor for you. And there's a single case where you might need to declare your own destructor if you're implementing a base class in an object-oriented hierarchy with virtual member functions, and you want to manage those objects with a unique pointer and not only with a shared pointer. Then your base class destructor has to be declared virtual, but you define it in a way where you say equals default. I have to write that down. So the only thing that I allow you is for a class X, only in special cases. You have a hierarchy and x is a base class, you write virtual tilde x equals default. All the other signatures don't belong in your classes. Let the compiler generate the code correctly for you. Now those who have written deliberately a copy constructor and copy assignment operator and virtual destructors might ask, how can I do that? Someone told me I have to provide all three of these in the past to my classes. And my answer is, write code in a way that you don't need to. Let's skip that text slide. Come on. Anything I need to say? Yeah. And there's another thing where when you define your own a single constructor in a class, you lose the default constructor. And if you want to resurrect that default constructor, which is a constructor without any parameters, the syntax to do that today is your default constructor. So your default constructor of your class. And that's useful only first if you have a default construction, a default version of your member variables as well that makes useful, supports the class invariant. You might need to use that if you have, let's say, a vector of these things and want to pre-allocate a vector with n elements. Not necessarily required, but in many cases it's useful to have a default constructor to avoid surprises on compilation. And with the default member initializers, you can even specify that if the members don't have to have their default value, but a specific value that we provide with default member initializers. These curly braces at the member variables. Who of you knows what I mean by this? Unwanted type conversions can be annoying when using built-in parameters and overloaded functions. That's a bad sentence. I remember what I wanted to say about that, but who knows what these unwanted type conversions, when these can happen? Yeah, there.
Every time you have a function which returns a type which can something which can be converted to a bool, for example, automatically, and then the compiler will say, you need a bool here, and it will convert it for you.
And what with your class types?
I beg your pardon?
If you have a class type X, how do you prevent these unwanted type conversions?
Well, you could I forget now. You define an operator for the conversion to bool specifically, or you tell us.
You were close. C++ has let's say, the benefit of providing automatic type conversion and applying those whenever you seem to ask the compiler to do so, and it might do so even without you intending to ask, but you ask for it. And the thing is, whenever you have a unary constructor, X taking a single type, let's say X, whatever that is, any value that is of that type can be automatically converted to X, to an X. These unary constructors are those that happen to be applied by the compiler if you call something that requires an X and pass something that is of this type. So if you have a unary constructor, in most, or let's say in more than 90% of the cases, in my opinion, you have to specify this constructor as explicit. If you specify these single argument constructors as explicit and do that deliberately, you will prevent the compiler from applying these constructors automatically on conversion of values. And the other way around that you were referring to, if you have a type conversion operator to any type, with C++11, you can also make that type conversion operator explicit, which wasn't available before. People were using overloading operator void star to have a bool conversion, for example, that wouldn't participate in any kind of strange integer arithmetic, for example, which a non-explicit operator bool would participate. So you can add something to, let's say, use an iStream and adding a 5 if the iStream would have a non-explicit operator bool overload. One thing that's also could be annoying if you have, let's say, many means to construct a type, which might not be a good design anyway, but there might be situations where you have different means to construct something. And if you have many overloaded constructors, that ends up to be annoying because you might want to need to specify the same things over and over again and have code duplication. That's something new in C++11. We got delegating constructors, so we can have one constructor that is used from all the other constructors that does the real work, and that's something that came with C++11. If you look closely in the standard, at least in the C++11 standard, I'm not sure if it got more or less in C++14, there are 7 pages of rules for when the compiler provides which kind of special member functions. All of these in these red don't do that signs. It's very hard to know them and to apply them correctly and know all the details of any special cases. And that's why I argue, don't write them yourself, let the compiler figure out it for you. It knows how to implement these 7 pages and will do that correctly for you. And also, the automatic provisioning of a copy constructor, if there's, for example, a destructor in your class, is deprecated more or less, or it will be deprecated. You don't get a move constructor from your class if you define your own destructor. Even if you default your own destructor, as I told you there, you will no longer be able to move your classes. That's why I say don't do that. So what can you do? Keep all member variables just as value variables. If you actually need to refer to something that is placed on the heap, use shared pointer or unique pointer as member variables. And here you have to make a choice. If you use a shared pointer, you get a shallow copy, because a copy of your object will refer to the same. If you use unique pointer, you will no longer be able to copy your object because only one unique pointer can exist, but you will get a move constructor in your object automatically if you use a unique pointer member variable. Don't do your own memory management, then you don't need to have this destructor implemented yourself. Let your member variables, shared pointer and unique pointer, do that for you. So the answer is use containers, strings, and smart pointers for resources, and let the compiler do the right thing for you in your code. So I call that the rule of 0. It's not only me telling that, but when I wrote that slide, I was the only one that was really shouting about that. Others are saying, oh, there was a rule of 3. Anybody heard about the rule of 3? There were some people claiming to have read Scott Meyer's Effective C++. There is the rule of 3 in there. You no longer do the rule of 3 or 5. Just write your code that the compiler generated special member functions with either copy, move construction, and assignment, and destructor are just the way you would have liked them to be. No special cases, no manual resource management. And if you need to have resource management, use either container classes from the standard library or smart pointers to do that for you. Not DIY. And if you really, really have something, go to Mauro and let him do it for you and use his classes, or whoever is providing your library. I just wanted to switch over to another slide set. No.
Well, if I can add something, don't come to me, but when you work with the different architectures like GPUs that are kind of reluctant in dealing with any stud functions, then you need at some point to do your own memory management, but you can design this in a way that it will be hidden somewhere, so it will be done once and for all, hopefully. You don't have to carry around too many of these pointers. But certain architectures forces you to go a little bit down the pit. So. And hopefully this will be fixed with the new CUDA version that apparently is capable of dealing with the stud namespace better.
But even with the classic CUDA API, you can wrap the CUDA functionality in your own resource management classes and
Yes,
don't
absolutely.
need to manually allocate on device and tree on device and things like that. You can wrap that in classes that actually are allowed to overload, to implement the destructor. But you do that once and call them.
Yes, you just build it once, and you're done, and you hopefully forget about those things.
Now, I take some slides from my lecture, and it goes a little bit out of, but maybe creating functions is one of the means of abstracting things. And abstraction means I have some pieces of code that I give a new name and just use a name from then on. And naming is good, and a good function does one thing well, and is named what it does, after what it does, and it has so-called high cohesion. Anybody heard of high cohesion? No, that's a computer science term. It means it also comes under the single responsibility principle, that an abstraction should just have one responsibility or one reason to change, sometimes named that way. A good function usually has only a few parameters. Anything more than 3 is doubtful. In some cases, we see that we have functions with more than 3, even in the standard library, but usually they come in some come in pairs, like a pair of iterators denoting a range. So actually, it's only a single parameter. It just happens to be syntactically true. And a good function also provides a guarantee about its result, a post condition, and maybe preconditions on its function arguments. And it's easy to use, either with all possible argument values or a consistent error reporting if argument values are outside of the preconditions. Consistent doesn't mean always safe. Consistent could also mean undefined behavior, which might mean you get pink elephants raining from the ceiling, or your hard disk reformatted, or your GPU is destroyed, hardware destroyed, which could happen. And if we look for class design, a good class is almost the same. It does one thing well and is named after that. It consists of member functions with only a few lines, without deeply nested control structures. I understand in some cases you might want that, but even then, with the inlining, you don't need to spell that nesting out in source code directly. And a good class provides a guarantee about its state, a class invariant. So either, let's say, the values are never negative or whatever. If you provide a date class, the dates are always valid date values. And also a good class, and that's occurs, some APIs actually make is useful without following a complicated protocol. Anytime you need, let's say, a user manual to a library that says to you, first to this, then to that, then to that, then to that, and if you mix up the sequence, anything can happen, that's a very bad API design. So stateful APIs where you have to provide these stages one after the other, I always ask why it's not a single function that I call and does everything right. And that should be the constructor if I use a value of that type. So anything that has a complicated protocol is bad, especially sequence requirements. Just to give you a little bit of syntactical sugar, struct and class are almost identical to use in C++. The only difference is a default visibility of the members that come after the opening brace. If I use struct, all members are public unless I specify private or protected. If I use class, all members are private unless I specify public or protected. So the two grayish looking boxes that are maybe grayish on my slide as well actually define the same thing, and after a class definition you put a semicolon. Anybody forgot a semicolon in his life? You know, interesting things happens, especially if that's in a header file and you include it somewhere else. Even more interesting error messages might happen somewhere else, and you look after that. Fortunately, modern IDEs place, whenever you write struct and a curly brace, it will place a semicolon right afterwards without you have to think about that. A constructor that you write needs to initialize the member variables in the sequence they are defined. Even if you spell out the names in the different orders, they will be reordered so they are initialized in the sequence they are defined within the class. And a good constructor will actually check for validity at construction time and throw an exception if the constructor arguments don't match, so it cannot construct the object, a valid object. That way you prohibit violating a class invariant. If you happen to use class libraries that require you to call an init function or initialize function after you created a class, that's a bad design. That's design of the 90s when we didn't have exceptions yet in some environments. So except for some very peculiar places, you will want to construct the correct object after your constructor is done. What did I show here? Let's see. I should get rid of that burning animation. Once you have a box with that, you copy that box around and forget to change it. So that's the class of the public. And what did I change here? That's old syntax, round parentheses, new syntax, curly braces. Both are valid. Curly braces are more modern. When I define a class, I define a type. And the good thing is C++ allows us to define such types as efficient as built-in types. Modulo some compiler some bad compilers not compiling them exactly as efficient. Especially Microsoft compiler is guilty of that. But in principle, I can construct types that are as efficient as built-in ones, with different semantics and other things. The default behavior of the C++ mechanics is, if you define a class type, to define value types. What is a value type? A value just exists. It can be copied, so you can have variables keeping a value of that. You can change the values of a variable, but it's still a value. You can pass it by copying things around. So the default behavior of C++ is actually for value types. And that's a good thing. especially you folks, you compute with values. Do you? Most of them? Yeah. If you happen to know a language, anybody a Java programmer here? A few one? C#? In Java, everything is an object, except for a few non-object types. In C#, you have a little bit more fine-grained control, but in C++, everything is a value unless you refer to it by reference or with a pointer. That's a distinction. In Java, everything is an object, so you refer to it by pointers, which are called references in Java, but aren't. The significance of the type is given by its member functions, functions taking the type as parameter type or return type, and sometimes the member variables. Most of the time, your member variables will be private, so you guarantee the values by only applying the functions that use the type, but that's a typical situation. Directly fiddling with member variable values from outside of a class type, I would say, is only allowed if you don't give any value guarantees of any kind of class invariant that might be violated through that. Also, what you shouldn't do, that's something not on the slide, who has written a set and get member function pair to member variables in? Named set and get? Set blah, get blah? Don't. That's a very bad practice. Because if you have something like that without any further checks and use set and get deliberately or freely, then you could just make your member variable public and be honest about it. If you have set and get member function and use them throughout your code, means that you have code that's in the wrong place. You have code that's calling to the guts of an object, doing something to them, to the guts, that doesn't belong to the object or to the class. That's no good design. And usually, when you have something that changes something to an object, it shouldn't be named set something, but actually name what the change means to that object. For example, let's say in the standard library you have you can change the capacity of a vector, and it's called reserve. That reserves more space. To check the capacity, it's not called set capacity and get capacity. So it's called reserve and capacity to check the capacity. That's the difference. And there was a question?
Well, maybe you already provided the answer, because my question is that it's not like having a public data member if I use a set method that also changes the status of my class accordingly to the, let's say, to the operation that I made with that set. But that's exactly what you mean with a reserve or a resize or something like that. It's not a set size, it's a resize. Okay, so
that's exactly you have to give it a meaningful name. Just setting a member variable, first it exposes that there exists such a thing, which you might no longer change afterwards. And second, you didn't think hard enough about the actual semantics of your type. So, a little bit of software engineering knowledge to the physicists. Yeah, a little bit about value characteristics. If anybody is doing OO programming a lot, object-oriented programming, heard about object-oriented programming, Python programmer. In Python, everything is an object as well. And there are 3 dimensions, so I'm not very good in drawing things, so I made it not really very nice, not very perspective. The most important thing, or very often the most important thing, is the behavior of an object. Another, often less important, or at least encapsulated thing, is the state of an object. And the third thing is the identity. And depending on how important each of these dimensions is, the classes that represent such objects have a different kind of significance. usually in C++, the identity is unimportant because it's given by, when the identity is important, I have to have a shared pointer or a pointer or a reference to something. And more important is the behavior and the state. If only the behavior and state is important, then we say it's a value object. Because if I have 42 in this hand and 42 in this hand, both would compare equally, even though there are two different versions of that 42 around here. So that's what I call a value. Everything that works like an int or a number, that is what I call as a value object. There are objects that are stateless and don't have state, and they make sense in C++ because they might still capture an abstraction and provide behavior for that abstraction, and also provide a different type that is distinct from something else. And it's the 3 dimensions. Okay, so value and behavior are the important parts of the C++ classes, and identity is usually less important unless the class is representing a reference like shared pointer itself. If you implement something like shared pointer, there the identity of the pointee is actually the important part. What's that? Let me skip that in the moment. Yeah, now that's not what I wanted to show you. You can self-study slides. Oh, maybe some guidelines. In C++, you can overload almost all operators with your own types. If you overload your own operators, which makes it possible to actually use your class types the same as you would use built-in numbers, for example, then try to not to be too clever. There are class libraries around that overload operators to provide very interesting effects like expression templates, which can have their use in some cases, but when things get wrong because you make a mistake, the compile errors might look horribly. And if you provide your own types with overloaded operators, then follow Scott Meyer's guideline. When in doubt, do as the ints do. So if you overload the plus operator, binary plus operator, you better add whatever your type represents and not subtract it or divide it, which is easily doable. But again, simplify and don't obfuscate. There are some operators where the standard versions actually have a specific sequencing semantics. So the logical AND, the right-hand side is only evaluated if the left-hand side of the AND is actually true. The logical OR is only evaluated the right-hand side when the left-hand side is false. The comma operator, the left-hand side is always evaluated first, and then the right-hand side. Whenever you overload these operators, which is doable for your own classes, you lose that left before right evaluation ability, because they are now regular function calls, and all function arguments are evaluated in some unsequenced order and passed to your function. If you overload operators, especially arithmetic ones, you better overload them consistently. Like if you overload operator plus, you might also want to overload operator plus equals. And it's even better to implement plus equals and let operator plus be generated for you by using the boost operators HPP library, which provides all kinds of automatic operator inclusion if you just define the basic ones. Like if you define plus equals, you get the plus operator for free. If you implement operator less than, you get all the other relational operators for free. If you implement operator equals equals, you get not equals for free. And if you define prefix plus plus, you get postfix plus plus for free, for example. And also consistent. If A is unequal to B, should exactly have the same result as not A equals B. And that's also how the boost operators library would implement it for you if you do the right things. And also symmetric operators that are symmetric with numbers should also behave symmetrically with your types. Templates. When is coffee break? 3:30 or 3? Huh? Us? Let's get started with templates. The original motivation for templates was actually to write containers like vector and only write them once and have the rest of the code generated. Very early implementations were actually using macros to create something like vector. There have been libraries still used very well into the 90s that actually refrained from using templates and used macros for generating generic things like a vector and other container-like things. So the idea became, okay, Bjarne came up with the idea, okay, we want parameterized types and type parameterized functions, and without copy-paste and all without the curse of macros. Macros have no more uses in C++ except for unit testing and for include guards. No more other uses of macros. And if you still have macros in your code, use develop to get rid of them, either by replacing them with const expr functions or constant definitions, or by inlining the code individually where the macro is called. Possible. You can even get that mass inlined if you want to. What we also get is we get different behavior based on types or other compile time parameters at compile time. So we can get compile time polymorphism. What is polymorphism? I write a piece of code, a single piece of code that behaves differently depending on what arguments I pass in. And those arguments I can pass in at runtime, usually by references or pointers, or I can pass them in at compile time, and that would mean I pass them in the angle brackets of a template, or in the function templates as just regular types of the function arguments. Just as an example, you can actually, with templates, you can reuse code that has not been written yet. For example, vector was written well before your own class, but you still, if your class fulfills the concepts of the vector template parameter, you can still create a vector with your class as an element type, and it works. There are a lot of template myths. One reason is many compilers in the early days and implemented templates very badly. People were unused, let's say at least those not reading a lot of French literature, were unused to the angle brackets. I believe in French you use angle brackets, I'm not sure in Italian. Do you use the angle brackets as quotation marks?
Yes, and in a book, when someone speaks, we use a kind of double angle brackets.
Okay, so in German it's and English it's not that used for that. You have the regular quotes, and people were afraid of space overhead, compile overhead. Well, the space overhead is no longer that big issue because we got gigabytes now everywhere, even in a mobile phone. And the compiler messages were confusing. Some of them are still confusing, but usually there are, you might get an error in the definition, but the reason you get, or the error message you get is as a place of the use of a template, but that changed a lot, especially the Clang compiler helped GCC people to improve their compiler as well. Clang tried hard to have good compile error messages, and that helped improving GCC as well. There are also compilers, some still in use, even illegally, like the Microsoft Visual Studio 6, never implemented templates correctly. And even the current Visual Studio, I haven't checked the last versions, but I believe they still don't do exactly what is said in the standard with templates, Microsoft compilers. And that's the main reason is they have one of the oldest code bases for their compiler, and they even hired a lot of bright people recently, or over the last 3 years, to get rid of these problems, but working with an old code base from the 90s or even 80s is quite a challenge. And there are some limitations in the usage, mainly for historical reasons. Some of them were, let's say, removed in C++11, but not all of them. And most of the limitations were there because the compiler vendors objected to have, let's say, a consistent orthogonal definition, because they were afraid they were not be able to implement that. And there have even been things around templates that have never been implemented but standardized. Like there was a keyword export that nobody actually implemented and nobody actually made use of, and that got removed as well again. So that's where the standardization committee learned not to standardize something without implementation experience. It still happens, but much less than before. Just to give you an example of why we would want to have function templates. See, we have a namespace with two functions called min, taking the minimum of two values. And if you look closely, you see that the function bodies are exactly the same. Even the parameters and the rest of the function looks the same, except for the types that are different. And this observation actually helps us. Even if we go down to and using strings, the body still looks the same, because the string provides an overloaded less than operator, and we can use that. And if we have these identical function bodies, and it's not easily extendable, if we want to use, let's say, unsigned values, we could call it. We might get ambiguities. You might get interesting results, because depending on what kind of unsigned types, it might promote to double or not. So that's all kind of bad things happen, because we always have to spell out the implicit set or an explicit set of overloads. Function overloading is nice, but if it's bad if we have ambiguities, or bad if we miss out one case in our overloads. And again, the automatic conversions that might happen underneath also provide some bad things. And I say show main, so I better show you main, otherwise I don't keep my promises there on my slides. I need to switch here. So that's the code that we just have seen on my slide. And now let's look at the main program doing that. And you see my code is not C++11 here. I get all these green stars where I should curly braces instead of equal. Well, let's ignore that for now. When we call min here, and if I place the cursor there, excuse the bigness of the cursor, the compiler will show me which overload actually got selected in that case, and that's the int overload. If I call min here with two double values, pi and e, it will show me the double overload. If I do the same with strings, I will also show me the string overload. If I call min with an int and pi, it will not show me the overload because it's ambiguous. It can either convert the 2, which is an int, to a double and call the min version with the two double values, or it could convert the pi to an int, which would be 3, and call the min with the int version. Since both conversions are one step, And each reach to a valid function calls is ambiguous because I couldn't tell the compiler which version I would want to call. I can get rid of that problem by casting actually to a double. It's a static cast. And then the compiler will select again the double version of my min function. And if I call min with two string literals, because they convert automatically to std string, I get the min call to the string version as well. And if I save that and compile that and let it run, I get exactly what I expected. The minimum of 88 and 42 is 42, of E and pi is E, of hallo, halli, hallo is actually halli, hallo, because the lexicographical ordering of halli, hallo is before hallo. And the minimum of Tony and Peter is Peter, because P is before T in the alphabet. And I think with that tension, it's a perfect time for a break now. Because now you are motivated to come back after break.